Hi, this video we're going to talking about 2D equilibrium, and we have talked about this topic before when we have two equations, force at x and forces at y direction, we sum up equal to 0. And thinking about for those problems, we have pretty much all forces going through the same point, right? They're going through this point O. Then we balance those four forces, for example. But now we're going to looking at potentially like this example. You have this crane here, and those are forces acting at different point. You know, for example, this is the weight of the crane, and there's a weight of the crate. They are the two different points. So for that situation, we're going to add our third equation. We're going to have to do moment. And here, we're going to do moment about any point. Because if you randomly choose a point, and if sum of the moment equal to 0, then we know it's at equilibrium. So you have to have the moment at any point that have to be equal to 0. So those are our three equations to solve the equilibrium problem, okay? All right, so we're going to use this example. First step is we're going to draw our FBD. They said that this fixed crane has a mass of 1,000 kilograms. So in that situation, our weight is going to be 1,000 times 9.8. That's 9,800 Newton. They used to lift this 2,400 kilogram of crate. So we're going to call this W1. This will be W2. Put in the calculator 2,400 times 9.8. That will give us 2,350 Newton. Okay. Then it is held in place by pin A. Pin A, so we know the reaction support will be have both x direction and y direction. Since it cannot move freely on either of those two directions, we label as AX and AY. B is a rocker. Since B can move freely at y direction for this situation, right? However, it cannot move horizontally. So we are going to have a reaction support at B, and we're going to call B x direction. So those three, AX, AY, and BX, are going to be our three unknowns. The center of gravity of crane is located at G, which you already used that information. They determine the components of reactions at A and B, which means they are asking AX, AY, and BX. Those are the three unknowns. So think about it. We have three equations so far, right? Fx, Fy, and a moment. Then we can go ahead and solve those three unknowns. So that's a typical how 2D equilibrium work. Three equations, three unknown. Now we have our FBD as our first step. Now we're going to write down our equations. Forces at the x direction. So in other words, all the forces at the x direction, we're going to put it together. We have AX, right? We will not have AY since it's at y direction, but we will have BX. That's x direction. That's all we have, right? Equal to 0. And there's no forces that's slanted direction. We don't need to decompose, right? Then Fy, all the forces at y. So we notice AY is going up, so it's positive. Then we also have this weight of the crane going downward, so it's minus 9,800. We also have the weight of the crate going downward, 23520. That equals 0. Okay, so we'll have our equation 1, equation 2. Obviously, you can solve equation 2 here. Then we're going to do our moment. Remember, it's at any point. So here, the rule of thumb is you choose a point that has a lot of forces. So here is a little tip. Choose the point where a lot of forces on it. Why? Because for this example would be A, because AX and AY, there are two forces, right? Why do we choose that instead of B and G, for example? Because in our moment equation, AX and AY going through point A, then the moment of this force rotating about A will be 0, right? Because moment of arm is 0. So then we're going to, for this moment equation, what that is we have to consider all the forces rotating about A. So this FBD, we have 4 forces. We already considered AX and AY. So for example, what we're doing is going to be moment of this AX force rotating about A. Then we're also going to rotate, thinking about all the force AY. This is the second force. And then we'll also have what? BX rotating about A. What other forces? We'll have W1 rotating about A. Also W2 rotating about A. So that's considered all the forces rotating about A. That's the moment. Now let's continue to solve this moment equation. So for this MA, we know that's equal to 0, that's equal to 0 because AX, AY going through point A. Now we're just going to consider all those 3. First, now let's look at BX rotating about A. So BX is a horizontal force, so we do not know BX, so write down BX. And the moment of arm, because it's force times moment of arm for BX rotating about A will be labeled as in this blue, right? So that's 1.5. This is a horizontal force, so moment of arm will be vertical. Then thinking about it, this rotation is going to be counterclockwise rotation, so it would be positive. Now we're going to consider our second moment, the weight. Weight is 9,800 rotating about A right here. So if we were to consider the moment of arm, it's going to be perpendicular distance to the force will be that. So the distance will be our 2 meter. And now let's thinking about the direction. The weight rotating about A, that's going to be clockwise rotation. So that's negative. Now let's look at the last one. So we have the weight of a crate. Force is 23,520 Newton. And moment of arm, again, from A is going to be, in purple would be this, right? That's going to be our moment of arm. And that distance will be 2 plus 4. And that rotation, rotating about A, it's also clockwise rotation. So that's going to be negative. All of those together, that's going to give us equal to 0. So we have our third equation. So the rest is we're going to go ahead and solve those 3 equations. Here I'm going to just write again so you can see better. So fx, we have ax plus bx equal to 0. Forces at y, we'll have ay. We can put all those constants to the right-hand equation. So 23,520 plus 9,800. Then we got 3,320 Newton. So we solve our AY. And our last equation, which is our moment equation, consider all the forces rotating about that point you choose. First one term is 1.5 bx. The rest is then 23,520 times our 6. Then we have 141 120, that equal to 0. Okay, so here you can go ahead and solve bx. You can do that. Here I want you pause for a second. You have three equations. We are lucky we got very three simple equations to solve, but sometimes you will get more complex. So go ahead, remember you use systematic equation, which we did before. Either you use your calculator or we use the online calculator to solve it. Okay, so here pause, trying to get your answers. So you can go ahead to solve this by hand for this particular problem, but I also want you to be very comfortable using this linear equation. Either you are using calculator or online Wolfram Alpha. So here I'm using the linear equations solver on Wolfram Alpha. We put those equations here, ax plus bx. So I'm using a and b represent ax and bx. And here for ay, since I cannot use two letters to consider to define a variable, I cannot use ay, so I'm just going to use y to be. I will make a note, say y means ay. So y equal to this value. Then the third equation is 1.5 times bx minus 19600, okay, etc. So then go ahead and solve. We have our answer here. So I'm going to take a note. Let's see. Take a picture, and I'm going back to my note. So from all this, what we calculated is our AX is equal to negative 107,147 Newton, and our BX is equal to the same value but opposite sign, and our AY is 33320 Newton. All right, so as right now you actually finished solving your problem. Here, make a note again, you get a negative value here. So what that means is AX direction, the true direction, is not going to be pointing to the left, to the right. It's actually pointing to the left. But we're gonna stay with this because our FBD is pointing to the right and our answer give us negative, which means together already show us AX gonna pointing to the left. So that's all. Just leave as it is. All right, so that's all for this problem. I'll see you next time. Bye.